Hey Tech Warriors, welcome back to Code Tech Chronicles. I'm your host Shashi Devendra, and today we are exploring two game changing data structures, graph and heaps. Whether you are prepping for interviews or building scalable systems, mastering these is must. Buckle up, we are diving into two these structures power everything from Google Maps to priority scheduling. Let's kick things off with graphs. What is a graph? A graph is a non-linear data structure made up of nodes, also called vertices and edges, connection between nodes. Graphs comes in many forms. Directed, where edges have direction, versus undirected. Weighted, where edges have cost, versus unweighted. Some real-world examples are social networks, like your friends' connections, navigation systems like shortest route between cities, web crawlers like site link structures. Graph representations. There are two main ways to represent graphs. Adjacency matrix, a 2D array where say matrix ij equals to 1 if there is a connection or 0 if there is not. Simple to use but waste spaces in sparse graphs. Second, adjacency list. Each node stores a list of its neighbors, more memory efficient, especially for large sparse graphs. Pro tip, use metrics for dense graphs and list for sparse graphs. Graph traversal. To work with graphs, you must traverse them. The two most important travel strategies are breadth first search, BFS, where level by level exploration using queue, and DFS, depth first search, deep dive along a path using recursion or stack. These helps us solve shortest path algorithms, connectivity problems, detecting cycles, finding components. BFS, breadth first search. In BFS, we use queue to explore all neighbors of the nodes before going deeper. It's ideal for finding shortest path in unweighted graphs, layered exploration like social network or web crawling. An example use case is finding the shortest connection between two people on LinkedIn. DFS, depth first search. DFS is the opposite of BFS. It uses a stack or recursion to explore one path fully before backtracking. DFS is great for detecting cycles, exploring disconnected components, doing topological sorting. Think of DFS like exploring a maze. Go deeper, then backtrack if you hit a wall. A practice problem. Cycle detection is a classic interview question. In undirected graphs, use DFS with visited set and parent tracking. In directed graph, use recursion stack or Kahn's algorithm topological sort. Interview tip, be ready to implement both versions and explain your logic. Now let's move into heaps. What is a heap? Another powerful data structure. A heap is a complete binary tree that follows the following properties. Min heap, parent is smaller than the children's. Max heap, parent is larger than children. Built on heaps is the priority queue, where elements are served based on priority, not just order. A real life analogy, think of the triage in a hospital or task management in an operating system. Min heap versus max heap. Here's the difference. In min heap, smallest value is always at the top. In max heap, the largest value is at the top. Use min heap when you want the next smallest item quickly. Example, Dijkstra's algorithm. Use max heap for ranking, like in the leaderboards or a high score. Heap operations. Let's talk about what you can do with heaps. You can insert or push, add a new element and bubble up. You can delete or pop, remove the top element and replace with the last, then bubble down. Peek, view the top without removing it. Heapify, convert an array into a heap in O n time. All of these happen in O log n time, making heap super efficient. Practice problem with heap. Kth largest element, use min heap for size k. Heap sort, turn array into a max heap, repeatedly extract top. Merge k sorted list, use the min heap to pick the smallest item from the multiple sources. These are very popular interview questions. Let's recap graphs. It consists of vertices and edges, types directed, undirected, and weighted, unweighted, represented using adjacency list or matrix. For traversal, we use BSF using queues or DFS using stacks or recursion. Key problems we solve with it is cycle detection, shortest path, and component discovery. And now heaps. Complete binary trees with heap property. Min heap is smallest at root, max heap is largest at root. Underlie priority queue, efficient O log n insert and delete. And key problems we solve are kth largest, heap sort, and merge k lists. Thank you so much for joining me on this deep dive into graphs and heaps. If this video helped you, give it a thumbs up, hit that subscribe button, and share it with your fellow coders. Remember, small steps, big impact. Stay curious and stay consistent. I'll catch you in the next episode of Code Tech.